In this video, we'll talk about solubility and go through the solubility rules. Before we start talking about solubility, we need to go through a few definitions. First, when we look at a solution is defined as a homogeneous mixture of two or more pure substances. And within that mixture, we have a solvent and a solute. The solvent is the one that is present in the greatest abundance. Everything else is a solute. And we always make a solution by dissolving the solute into the solvent. And one important note, when the water is the solvent, we call that an aqueous solution. And a lot of the times in chemistry, we use aqueous solutions when we're doing our reactions. And now a few definitions about solubility. A compound is soluble in a particular liquid if it dissolves in that liquid. A compound is considered insoluble if it does not dissolve. And an aqueous solution is the homogeneous mixture with water. And in this class, we'll be focusing on ionic compounds. And when an ionic compound dissolves in water, it usually dissociates into its corresponding ions. So if we take sodium chloride and I dissolve it in water, it's going to separate into a sodium ion and a chlorine ion. And both of those, their phase changes from solid into an aqueous form since it got dissolved in water. So looking a little closer at this dissolving process. When we look at a water molecule, water is consistent of an oxygen bonded to two hydrogens. That oxygen has a slightly partial negative charge. It's slightly negative on that side. And the hydrogen side is slightly positive. This is how water is a polar molecule. So what happens when we take salt and we dissolve it in water is the water molecules actually start to pull off the individual ions from the salt crystal. If it's a sodium, the purple here, it's going to have the oxygens pointing towards it. Since the oxygens are partial negative and the sodium's positive, they're going to help stabilize each other with opposite charges. Same thing happens with the chlorine. The chlorines will start getting pulled off and the water molecules will surround them with the hydrogens pointing towards it. So that way the negative charge on the chlorine is stabilized by the slightly positive charge on the hydrogens. And this is how water starts to dissolve compounds. It'll start to solvate it or have water molecules surround the individual ions. And so we can see when something is dissolved in water, it splits apart into its individual ions. Here we have silver nitrate. If I take silver nitrate and I dissolve it, I'll get a silver ion and then I'll get a nitrate ion. Notice the nitrate, the polyatomic ion, stays as an NO3. It stays as that polyatomic ion unit. It doesn't split apart into nitrogens or oxygens. And if we had something like calcium chloride, which is CaCl2, that'll split apart into a calcium ion and two chlorine ions. So notice the 2 down here becomes a coefficient of a 2. So this means we have 1 calcium ion and 2 chlorine ions when we take a calcium chloride and dissolve it in water. When something is considered insoluble, that means it does not dissolve. The water will not start to pull off the ions and hydrate them. So instead what happens is it stays as a crystal in the bottom of the flask. An example of this is silver chloride. Silver chloride does not dissolve in water. So that means if we take silver chloride and we put in a beaker of water, it's going to stay a solid on the bottom of the beaker. And so it does not dissolve into its independent ions, into its individual ions. So that's the difference between something being soluble and something being insoluble. The next question is, how do we know what's soluble or insoluble? For that, we want to look at the solubility guidelines. And with this chart here, we look at the at the soluble guidelines first. So example, if we have anything that's lithium, sodium, potassium, ammonium, nitrate, or acetate, if your ionic compound contains any of those ions, then it's going to be soluble. And remember, these are solubility guidelines for water. If your compound contains a chlorine, bromine, or iodine, it's usually going to be soluble. However, there are some exceptions. So the exceptions are silver, mercury +2, and lead +2. If you see a silver chloride or silver bromide, that's going to be insoluble. If you see a mercury chloride, that'll be insoluble. Or if you see a lead iodide, that would be insoluble. However, if you see an iron chloride, that would be soluble because iron is not one of our 3 exceptions. And then next we have our compounds containing sulfates. If it's a sulfate, it's usually soluble, unless it has calcium, strontium, barium, or lead. These are our exceptions. So again, if you have lead sulfate, that would be insoluble. But if you had iron sulfate, that would be soluble. So you can see there's going to be some exceptions to these rules, and these rules came about through observations. So that's why we have so many exceptions for these guidelines. And don't worry about memorizing the guidelines. You will be given a table to use during any exam, so don't stress about remembering them. A slightly neater form for figuring out the guidelines. If it's an alkali metal, so if it's part of group 1, it's going to be soluble. If it's ammonium, it's going to be soluble. If it's nitrate, acetate, or perchlorate, then it's going to be soluble. If it's chloride, bromide, or iodide, with these exceptions, as long as it's not one of these exceptions, then it'll be soluble. Sulfate, usually soluble, except for these exceptions. So here's a nice little list compared to the flowchart. Whichever one works best for you, go for that. So now that we've looked at the soluble ones, so now that we've looked at the soluble guidelines, let's look at the insoluble guidelines. So for insoluble, most compounds are considered insoluble if they contain a hydroxide. The exceptions, as you see, are lithium, sodium, potassium, and ammonium. So you can see it's group 1 and ammonium. So if you have a hydroxide that contains group 1 or ammonium, it'll be soluble. If it's kind of our heavier group 2, so calcium, strontium, barium, those will be a little bit soluble, but not much. Anything else will be considered insoluble. Same thing for sulfides. Sulfides are generally insoluble with these exceptions. Again, you can see it's group 1, ammonium, and kind of a heavy group 2. If it contains any of these, so example, if we had lithium sulfide, that would be soluble. However, if we did magnesium sulfide, that would be insoluble because magnesium is not one of our exceptions. Same thing for carbonates and phosphates. If it's a lithium carbonate, it'll be soluble. Sodium carbonate, soluble. However, if it's anything else besides lithium, sodium, potassium, or ammonium, it'll be insoluble. Hopefully you guys can see a trend with the insoluble ones. Anytime you see lithium, sodium, potassium, or ammonium, it'll be soluble. So anytime you see those, always soluble. Don't have to think about anything else. It's only the other ones that there could be some exceptions. But anytime you see these, always, always, always soluble. So again, here's a list of our insoluble ones. And it's important to note that the soluble guidelines always trump the insoluble guidelines. That's why the lithium, sodium, potassium, and ammonium are always soluble. So here, if it's a sulfide, carbonate, phosphate, hydroxide, or oxides, oxides act just like hydroxides. Group 1 and ammonium are always exceptions. And then the sulfides and the hydroxides or oxides, it's the heavy group 2s. So as you can see with the solubility rules, there's a lot of exceptions, but that's because the solubility rules come about from observations. So since they're very observation driven, that's why there's so many exceptions. But we want to use our solubility rules so we can determine if our compounds can dissolve in water. If we get our compounds to dissolve in water, that means we can then get a chemical reaction to occur. So the first step for chemical reactions most of the time is you need your compounds in their aqueous form. So hopefully we can use these solubility guidelines and then move forward and start looking at our different types of reactions.